Okay, let's just started recording. We talked about different privacy mechanisms or privacy enhancing technologies that mainly deals with data, right? So we started with what is that? K-anonymization, which are example of an uninteractive privacy, right? Where data is published or at least anonymized before publishing. And then we talked about interactive settings for data analysis, and that's being, differential privacy. And then after that, we started to talk about how to process data in a privacy preserving way, right? We had this homomorphic encryption schemes. Then we had the secure multi-party computation scheme, where we have multiple or a number of parties that would like to collaborate in order to compute certain function or evaluate some common function. The problem is there that each party don't want to share their private or confidential data with other parties. So we ended up with some protocols where Alice and Bob or Eve or Charlie or whatever, they communicate with each other, achieving a common goal of evaluating some function, right? We talked about the privacy of data, privacy of the functions, and so on. Now today we're going to switch or kind of have another aspect of privacy, which is what is called anonymous communication. So previously we were talking about data, privacy of data in storage or in processing. Now we're going to talk about data in transit, being transit or being exchanged from one party to another. So this is the outline. So we'll talk about communication anonymity, and then we'll talk about particular examples, anonymous remailers. You might, although these anonymous remailers might sound like a little bit conceptual and theoretical in the first time, but there are some applications, although very limited. But it's really important to understand it because that will lead us or give us a kind of a good introduction to a much more practical networks, which is called mixed networks, or sometimes they call it CHAMS, mixed network. Where CHAM is the David Cham is the guy who kind of created this type of network. So what do we mean? Why do we concern about privacy on public network? You know that internet is basically designed for or designed as a public network. Initially, it was mainly as a private network, being started from by this I think DoD or DARPA as a special project for military. But then they realized that this is actually a very good business tool, and it started to be publicized, right? So it is indeed a public network where anybody on the network, especially in your LAN, might see your traffic, might see what network routers do, and what do they actually store and forward from for the entire network. Now there are some, I would say, control security mechanisms, right, to make sure that such data is not leaked. But by design, all this information is actually public, right? So anybody with fairly good, let's say, background in networking, they can actually know what are the who are the senders and receivers for any IP packet, right? Okay, so even if we're concerned about the confidentiality of or privacy of the data, then encryption will not do. Encryption will achieve that, but still, even in these security protocol like IPsec, TLS, SSL, they only encrypt the content, but they are not. But you still can see the source, destination, and so on. Okay, so this might be an issue in terms of privacy. So think of an application where you really want to kind of browse certain website without anybody knowing what are you or who where are you browsing, and the browser itself or the page itself, you don't want the page itself that you are browsing track your movement within the page. So all these concerns can be considered as a privacy concerns for browsers. Now there are some also other advanced attacks, like for example what is called the timing attacks, side channel attacks, like knowing how much flow or how much data traffic is going from your connection within your connection to certain websites and so on. So there are so many attacks that can actually breach your privacy on the internet. Now let us just quickly understand how network protocol, how the internet works specifically. So you have an application message, and then on top of that you're gonna encapsulate it with what is called the transport header, basically, because you can multiplex multiple application in a connection, and for that you need to kind of map the process into the socket, right? And then you can interface it with the routing network. So you have the network header, and then on top of that you will have the link header and the link trailer in order to send it over a specific medium, like LAN or WAN or whatever. And on top of that you have obviously the physical channel. You see, this is the typical OSI network, right? You have an application, transport, I think I forgot what is it, medium, session, medium, and physical. And in each layer, you still can have encryption in order to kind of preserve, or not preserve, but save or hide the content from the attackers on the wire. Okay, so obviously you can actually hide the content of your message using encryption, and as well as there are some other techniques in order to hide the kind of other data or other information that can be observed using some traffic analysis. So this is in terms of what is called passive attackers, where they only can observe messages, like sniffers and so on. There are some attackers or attacking mechanisms that actually affect and inject kind of what they call it active attackers that can change and inject messages and destroy the original packets, modify it, fabricate it, and so on. And there are some other attackers that will the purpose or the objective is not to observe or to destroy your data, but more like compromise the nodes. And this is one of the strongest kind of attacks in network, where if somebody can compromise the node, then he can do both observe and as well as destroying and affecting the exchange messages. So as I said, encryption is a pretty common technique in order to guarantee or hide the content of the messages. And then you can do the encryption at many entry points, like at the link layer, network layer, transport layer, application layer. So how each one of those are done on each layer is not of our concern in this course, but I'm explaining this to tell you that there are some countermeasures that preserve the security of the content. By security, I mean the integrity and confidentiality. Because again, if you think about an attacker with the capability of changing or modifying and fabricating the packets, that's an integrity issue. While if somebody can observe the message content, that's a confidentiality issue. So you can also solve all these by using encryption at many layers, or kind of combination of all layers. Now, the problem with all these encryption techniques is that they do not hide identities. And by identities, I mean we still know who is the original or who is the sender and the receiver of such packets. So, for example, like IPsec and other security network security mechanisms, you still can get the IP address of the IPsec gateways, and we still can so do some trace back or trace routing in order to kind of reveal who is the sender and who is the receiver. Now, what we are concerned with is the user privacy in terms of hiding the content. Basically, that is, same as confidentiality. But we are also concerned about who is, who is originating these transactions and who is receiving such transactions. Okay. There are other application of privacy in communications, such as untraceable electronic mail, and sometimes you wonder why would you want to do such a thing. That is, it has its own applications in military, in some defense agencies, but also, it can be used as a safe medium for employees in a corporation or a corporate to, let's say, complain or kind of report some wrongdoing within the company. So it has actually, it does have some real application or real usage, and even in some business networks, right? Other techniques or commonly used anonymous communication is being used for now as a medium for interaction or communication in digital cash network. See, this rise of Bitcoin and other cryptocurrencies, it requires kind of anonymous communication between a sender and receiver, because after all, in the cryptocurrency, or the main benefit of cryptocurrency is, hiding out the details of any financial transaction between a buyer and a seller, right? So in some cryptocurrency network, they don't want the seller to know who is the buyer, and maybe vice versa. So the buyer is buying something, but he doesn't want the seller. And sometimes we are interested in hiding out who is buying from which seller. So kind of the relationship anonymity. And we're going to talk about it in a minute. Other techniques is using, the anonymous electronic voting, which we talked about, but now we are concerned about really more about from the communication or networking point of view. So these are the anonymity forms that we are concerned with. The recipient anonymity, we want to conceal or hide the identity of the message sender. Actually, this is wrong. Okay, we know who sent the message, but we don't know who received it. Okay, so we are concerned about the recipient anonymity. And actually, we can do that using simply or naively using the broadcast mechanism, right? So if you want, let's say I have a message that I want to send to a particular person within this class, okay? So what I do is I can announce this in publicly, like as a broadcast form. Now he will know the message, he will get the message, but anybody else within the group will not know who is the intended receiver, right? So this is a very simple example of kind of recipient anonymity. Now, if you think about this, is this really a good solution, an efficient solution to guarantee recipient anonymity? What do you think?
No, because it floods the network.
What, sorry?
No, because it floods the network.
Floods the network, right? So we have a scalability issue, right? So if we let's say we have 30 students here, so it might be feasible to send an email to 30 students or send kind of message. But how about if we have a large number of users? Yes, the privacy is is good, but you're gonna flood the network with so many messages that can be that are useless for most of the users. Anything else?
I think the message is available for all people on the network,
right,
to read.
Exactly. So how about if this message contains some confidential information about for the recipient, right? So you're solving one thing, but you are solving a problem with another problem, right? So what other technique can we do in order to guarantee the anonymity of a recipient? What do you think? Other than broadcasting. Anyone?
Send it to.
Yes, Khalid, go ahead.
Routing through multiple nodes. The way Tor uses it.
Okay, that's actually good. So why can we let's say, rather than having a full broadcast to all users, can we identify a small number of recipients and broadcast to this to this number? Okay, so that's one solution. Abdulaziz?
I'm not sure what Khalid, if it's the same as Khalid mentioned, but another solution is to use a trusted third node that for the packet to a specific recipient.
Exactly, yeah. So we have someone in the middle, that kind of proxy or a mediator that received this message, right, and kind of somehow send it to the recipient. Okay, only the middle one, the proxy knows who's the receiver. Okay, so there we have some few solutions. We're gonna go over kind of address or have or kind of talk about or discuss a technique that actually preserve the recipient anonymity. Obviously, if we have recipient anonymity, we also have the sender anonymity, right? Where we have we are not concerned about who received the message, or we know who received the message, but we don't want to know who sent the message. Okay, so for that there are one technique called the dynamic cryptographer DC network, and this is so dynamic cryptographer is a protocol. It's a very simple protocol that we can, if we have time, we're going to cover it because it's a little bit theoretical. I'll at least give you the framework, and then based on this framework, we can set up a network based on this concept or based on this framework for senders to send messages while preserving their anonymity, right? So we know we're gonna receive. We know who is the sender, we know who is the receiver of that message, but we don't know who actually sent that message. And by the way, it seems that recipient anonymity is there are some easy ways to achieve that. Sender anonymity is a little bit harder problem, trickier problem. If we have a trusted third party, that's fine. Then we can actually achieve both recipient and sender. But if we don't have that, it will be a little bit of difficult, right? And think about it like SMC. SMC, if we have a trusted third party, then everything is this is the ideal world, right? Everything is easy. But if we don't have that, then the sender anonymity is a little bit trickier. That's why there is actually a way, but it's a little bit more. I don't think we have time to cover it. I'll see if we have fairly good progress in this lecture. I'll just give you the idea of dynamic cryptography. And the last one is what is called message linkability, or I shouldn't call it message linkability, more like the recipient sender linkability, or kind of the relationship anonymity. Okay, so in other words, we know that there is a message, but we don't know who is the sender, who is the receiver. And for that, we will and for this particular type of anonymity, we're going to consider, or we're going to discuss a specific type of network called mix networks. Sometimes they call it CHOM mix networks. Sometimes they call it simply mix networks. Okay, so we'll talk about it inshallah during this class. But before talk about general communication, like or general network, like packet by packet kind of thing, let us talk about a little bit of a simpler case, and that is sending emails. Okay, so particularly we have just think about or consider the case of what is called email. And for that, there is a conceptual or a theoretical framework I'm saying theoretical and conceptual because it's, at least in theory, we can do that, but in practically it's a little bit of, there is a lot of overhead. So unless there is a need for such system like anonymous remailer in, let's say, a corporate or in a big network, it's not really, you know, like that practical, because the overhead is huge. Now, in anonymous remailer, the promise here is we're gonna send message anonymously. That is, both sender is anonymous as well as receiver is anonymous. Okay, and there are actually four types: type 0, 1, 2, 3, type 0, 1, 2, and 3. The first type 0, which is called pseudonymous remailer, and this is, you know, very basic, very simple, you know, naive approach using pseudonymity. Okay, so it goes in line with what Abdulaziz mentioned. If we have a trusted party that we can, you know, hide away the senders and receivers' true identity, then we can achieve this pseudonymity. The other one is what is called cypherpunk remailer, and then mixmaster and mixminion. So we'll not give so much time on mixmaster and mixminion. I'll just explain to you what they are doing, but we are mainly cover or talk about type 0 and 1. So in type 0, from the name, pseudonymous remailer, there is a trusted party or a remailer, okay, call it a remailer server, that will generate a pseudonym for each user. Okay, and it keeps this mapping, okay, from the true identity to the associated identity. Every time a sender want to receive or want to, you know, send an anonymous mail, it will send it to this remailer server, right? So the remailer will strip out the true identity and replace it with the anonymous ID or pseudonym ID. So for example, let's say my account is, let's say, mfilimban, and I want to send an anonymous message to you. So what I'm going to do is I'm going to contact this server, call it remailer server. I will, you know, the server will strip the header, right, and kind of change the source, or the, what they call it, the sender address, to some pseudonym, right? And then it will forward this email to the intended recipient. And on the other hand, if we, because this server or remailer will have such mapping between every identity and every associated identity, then it also can, you know, anonymize the receiver by using a fake or the pseudonym receiver ID, right? So again, don't be confused, because when I say recipient anonymity, I know who I'm going to send this message to, right? But I don't want the attacker from outside to know who actually received this, who has received this message. Okay, so from my side, I know, obviously, I know who I'm going to send this message to. But the recipient anonymity, meaning that outside, an attacker from outside the, if you remember, the system or the world, should not know who is the true receiver of this email. Make sense? Now, if obviously, if the recipient want to reply to this address, he will use the same address in the sender header, and the receiver, the remailer server will, you know, reverse the process. So in a nutshell, the type 0 or the pseudonymous remailer will use the pseudonyms, right, or pseudonyms for each user in order to hide away the correct or the true identity, right? So having this very simple remailer server, obviously it has many disadvantages. Okay, so I would like to know what is the main disadvantage in such system. Anyone? Let's talk about. Yes, go ahead.
Wouldn't it trust the third party, of course? If the third party was adversary,
Yes, it has to be trusted, right?
Yeah.
Okay. Right. So what does trusted third party entail?
That we assume that the third party will not go out of the, do not compromise the protocol and follow it.
Right. Okay. يعني meaning that whoever is administrating this remailer server should not go and check who is sending to whom, right? Or kind of do this mapping. Okay, so let's suppose that this trusted this server is trusted. Nobody is kind of unveiling any information. There's a problem, a bigger problem. Suppose that this is trusted. Now let me ask you this question, let me ask the same question in another format. What is the so in terms of privacy, it all relies on a single point of failure, right? In other words, this mapping is kept where? Say in a database. What happens if this database is being, leaked?
All the mappings will be revealed.
Exactly. So whoever get this mapping, he can figure out who sent what and who sent to whom and who is sending what. Right? So obviously that's why this is called type 0. This is a very naive approach because it kind of relies on something that is, as I said, a single point of failure that is very weak. And that's why they considered another type or kind of think about it as an improvement. Rather than using pseudonyms, they kind of use encryption. Okay? And the idea here is as the following. Rather than keeping or having this mapping between the true identity and the pseudonyms, we're gonna have any record. We're gonna do it on the fly. How is that? By using encryption. Okay. So the idea here is that we, in addition to encrypting the packets, right? We're gonna do it in a chain. Okay. And this chain is used to obfuscate the trail that is the route between the sender and the receiver. Okay, so let us think of an example. Now suppose that Bob want to send to Alice. Okay, so I think this should be using Bob's secret key. It shouldn't be private public key. So suppose that Alice. Actually, Alice is a public key. Should it be Bob's? Okay, sorry about this. So let's say Bob is trying to send to Alice, right? So he should use Alice public key to encrypt this message. Okay, and so he will actually.
Doctor, the public key will be the same for Bob and Alice. They agree on it. So it will not make any difference.
We are using public-private key.
Yeah, but
okay, if you're using secret key, then yeah, Bob and Alice will agree on it. But
for encryption, we will use the public key, and Alice and Bob will agree on the public key. So, it will make no difference.
Yeah, but that's called private key, right? So if let's say if Alice want to send something, Bob want to send something to Alice, so Bob will use the public key for Alice, and Alice will decrypt using her private key. Right?
Yes, right. But Alice and Bob have the same public key.
Okay.
So it will make no difference because they agree on
it. But how does Alice? Because how about the private key?
Well, the private key will be specified for both, Alice and Bob, and it's two different secret keys. No.
Sorry,
only one secret key.
I think no. For Bob and for Alice, each one of them have its own public and private key and secret key.
So it should be Alice. Sorry,
Okay.
should be Alice. Okay. So I think I'll fix this anyways. By the way, the slides are on Blackboard if you want to download it. So now okay. So in order for Alice, to Bob to send an email, so it will send to the remailer, right? But he will send it to the remailer using kind of some they agree in some certain protocol. So the way it works as the following. So he knows Bob wants to send to Alice, right? So he'll encrypt using Alice public key, and then he will append the header, the destination, which is to Alice, into the packet, and then encrypt the whole packet using the public key for the second remailer. Okay, we assume that we're going to use 2 remailers as a chain of 2. So we know all the public keys for all the remailers. So we're going to take the remailer number 2 public key and encrypt the original message, which is already encrypted, along with the destination, which is to Alice. And then on top of that, we're going to add the destination, okay, to which is sent to remailer number 2, and then we're going to encrypt it using the remailer 1's public key. And then we have one packet, right, or one message, and this message contains the instruction as well as the content. So the instruction in this particular message is after the remailer 1 will get this message, right? He will kind of decrypt it. He will decrypt it, and then he will find out. Oh no, the instruction is to send it to remailer number 2. Okay, and this message itself will be sent to remailer number 2, and then it will be decrypted again in order to get this message, which is encrypted, with the instruction to send to Alice. And then remailer number 2 obviously will send it to Alice, right? So now the idea here is as the following: who knows who is the sender? Who knows who is the receiver? If anybody kind of get into the remailer or any connection between the sender and the remailer, who is the? Do they know who is the sender? Who is the receiver? No, because that is kind of embedded in some encrypted messages, right? Now, on the other hand, if anybody checked this message, right, and the connection between the Bob and remailer number 2, does anybody know who is the sender? No, right? Except, so in other words, what I'm trying to say here is that neither the remailer number 1 or 2 knows who's the exact end-to-end or who is the pair of sender receiver. Okay, so remailer 1, obviously he knows, or it knows that this message is coming from Bob, but I don't know where is it going exactly, because it's going to remailer number 2. Now remailer number 2 knows that this message is going to Alice, but I don't know which sender it's coming from. So if the remailer 1 and remailer 2 themselves, they don't know who's the the pair, sender and receiver, then nobody else knows. And that is the idea of cypherpunk remailer, right? So that the idea here is to hide the sender anonymity from remailer 2 and the rest, and the recipient anonymity from remailer 1 and the rest, but also the pair, the relationship anonymity, right, from remailer 1, 2, as well as the other one. Does that make sense? Now, if it is still not clear, we have exactly the same example, but more kind of with more details when we talk about Chom's network. But this is the point here is that, in type 0, we are just relying on a single or kind of centralized server where it has this mapping between true identities and pseudonyms. In cypherpunk, we are kind of addressing that issue, by introducing encryption to packets or using the public-private key or PKI in order to communicate this message in anonymous way. Okay. Now, unfortunately, there are some attacks or there are some problems with this technique or this cypherpunk remailers. One of them is what is called timing attack. So if there is only one message that is being sent at a time, from remailer 2 to remailer 1 to Alice, right? If you observe what is coming in from remailer 1 and what is out from remailer 2, then you know who is the sender and who is the receiver. Make sense? So what I'm saying is, if you have this remailer, think about it as one entity. Although there are so many, intermediate servers. But think about it as a black box where some message is coming in, some message is coming out. So you know if there is Alice is sending a message to this black box or anonymous remailer, and there is only one packet going out to Bob, then you immediately know that Alice is sending something to Bob, right? So this is called kind of timing attack. So what is the solution for such an attack? What could be a good solution for this attack?
Broadcasting some dummy messages.
Okay, broadcasting some dummy messages. That could be a good solution. So if, let's say, if you receive one email or one packet, then you send multiple packets, right? But I know that Alice is sending now.
Alice could send number of messages with that.
Okay, so ask Alice to send number of messages. But suppose that Alice doesn't want to cooperate. And she's sending only one message, only one email. So one way to do it is hold that message. Don't send it immediately, or what is called batching. Use batch mixing, right? So hopefully, at some, if this remailer server service is big enough, hopefully within some time, if you hold this message for some time, you will receive more emails, right? The longer you wait, the more emails you get, the better the privacy, because the sender anonymity is getting larger now. Also, the anonymity set of the senders is getting larger. You agree?
Yes.
So this is the idea of kind of in order to address this timing attack. Hold the message. If you receive it, don't just send it right away. Hold it a little bit until you make sure that you receive a good number of messages. Mix them, send them back to their. When I say mix them, of course, kind of randomize their order and send them back to the intended receivers. Make sense? Now there is another challenge here. Even if you did this batching timing to adjust the timing attack, if I'm kind of sniffing or the channel of Alice, and I know that the message is of this size, particular size, okay, and I know how many anonymous remailers are in this service. And then what I can do is I can observe the channel going out to Bob, to Charlie, to whomever, and I can do some kind of footprint analysis, right? So we started, let's say, with 100 kilobytes, and I know there are some, let's say, two anonymous remailers. Each will strip out 20 kilobytes, and I see here 60 kilobytes. So this Alice, this message that's sent by Alice must be addressed to Bob. So there is the problem is not only timing attack, but also what? The size, right? The size attack. So this is kind of side channel attack. By observing the size of the packet, okay, the coming from Alice, and observing the packet that is going to Bob, I can kind of connect them together. So what do you think a solution for this? Yes, Abdulaziz.
Padding the message to be a fixed size with all
Exactly.
the messages.
Okay, so we have message padding. That's exactly what is the idea. In other words, rather than having varying size of messages or packets, let's make it uniform, right? The
Sir,
problem, yes, Yamin.
so if you pad with zeros or ones, couldn't you still tell like you have an abundant amount of zeros and ones in some header location?
But you're gonna do it in an encrypted format, so you wouldn't tell, right? So
okay.
only Bob will decrypt and see this pads. Right? Now, there are some performance issues with padding, obviously. For example, if you have, so the pad has to be as large as the smallest packet that you are sending, right? And obviously, if you have large packets, you have large. It will take more time to decrypt and encrypt and so on. So there are some overhead. So the other solution, which is kind of implemented, is what is called Type 2 remailer, Mixmaster, is to fragment the message in equally sized packets. Okay, and for each packet, you're gonna number it give it a unique ID, right? So you can do it. This fragmentation can be done either at the sender or the first remailer, the very first remailer. Okay, so it will kind of fragment the message and encrypt and do the magic and send it back to different remailers. The very last remailer that will send to the recipient will collect, right? So now what we are achieving here is to kind of nullify the attack that can be done on Cypherpunk in terms of timing as well as size. But what is the problem here? We are putting more overhead coming from fragmentation and defragmentation. How about if some fragments are being lost, so you have to add some protocol. That's why really Mixmaster remailer is conceptually it's very simple, right? Cypherpunk is very simple. Just encrypt, decrypt, send from remailer 2 to remailer 1, and so on. And Mixmaster is do fragmentation and reorder it. It is conceptually easy, but when it comes to practical, from practicality point of view, it's a lot of overhead just to send an email or so, right? So there must be other solutions. Type 3, which is nothing but so there are some associated attacks on Mixmaster remailer. Mixminion is just a better kind of an improvement over the Mixmaster, which makes it more practical. And it also adds the ability for the receiver to send a reply to the sender and so on. So it will nullify some of the replay attack and compromise attack, which are kind of part of the Mixmaster. Anyways, I'm not gonna give you details about Mixmaster and Mixminion because it will take us some time and deviate us from the kind of the more important content in this material. Anyways, so Mixminion remailer is actually very difficult to implement and is not being widely used. Mixmaster, yes, there are some feasible implementation for Mixmaster remailer. One of them is in I think in eBay. If you know eBay website, they use somehow kind of Mixmaster remailer. So the receiver doesn't know who is the sender doesn't know the receiver. Anybody else, it doesn't know who is sending to whom or who is buying something from whom. Okay, but that is has very limited functionality. But the idea here is as the following. You see, I already introduced to you this Cypherpunk or Cypherpunk remailers with the encryption scheme, right? By kind of encrypting or kind of putting layers of encryption on top of each other. Now, actually, this is an example of a bigger network or a bigger networking protocol, right? That is more commonly used for different applications, not only for sending email, but it's also used for, as I mentioned, in digital cash, in e-voting, and so on. And this network called CHARMS Mix Network. Sometimes they, as I said, they call it Mix Network. So Mix Network is a routing protocol that guarantees the relationship anonymity using intermediate proxies. That's why it's called Mix, because these proxies, they called it Mix. And for apparent reason, you will understand why it's called Mix or a mixer. Now, the main addition or the main guarantees or the main feature that Mix Network provide is not only to send a message anonymously or receive a message anonymously, but can establish a channel between sender and receiver. So if you want to send consequent messages between sender and receiver, you can actually have kind of think about it as a virtual link or a session between the sender and receiver. And you can have somehow bidirectional communication. So the sender can send to the receiver can reply back to the sender. And most commonly, CHARMS Mix Network is used where you don't have a single authority that controls the network itself. Okay, so if in terms of remailers, if you don't trust the mail delivery system in terms of tracking who is sent to whom and so on, so usually CHARMS Mix Network is used in place. So the basic network mix design is as the following: if Alice wants to send something to Bob, okay, let's consider this message in the middle. So what is this? What are we doing here? We are using the public key of Bob to encrypt some message M, and this is the message that is being sent, right? So M here is the message. I think there is a confusion here, but hopefully it will be clarified. So this M is the message that is being sent from Alice to Bob, where R0 is just salt, just random number padding. Okay, so just to avoid that side the size, the packet size type of attacks. And on top of that, we're gonna add two things. We're gonna add B, which is the address of Bob, the identity of Bob, and another random salt, and then encrypt all this by the public key of the mixer. So here, so the confusion here is I'll try to use the different notation. So PKM is nothing but the public key of the mixer, where a mixer is some proxy in the middle. Okay, is that clear? So what we're doing again, we are taking the message, we are padding it with some random number, we are encrypting it using Bob's public key, and then to that encrypted content we are adding B, which is the kind of the address of B, as well as some random number salt, and we're encrypting it using the public key of the mixer. Now, if this packet is received by the mixer, right, and let's say this mixer because it was encrypted using his public key, he will decrypt it, right, using his private key. So we'll get this message. Okay, and on top of that, he will get the receiver, right, which is Bob. So we'll basically forward this to Bob, right, and Bob will get the message. Make sense? So now, where is the anonymity? What is the anonymity coming from?
Sender anonymity.
So sender anonymity, at least, right? So now, in terms of this mixer, right? If somebody kind of, let's say, hacked this mixer and was able to let's say compromise or kind of has the private key for this mixer, so he will be able to get the address Bob, and he knows that it's received from Alice, right? So in other words, if we are back to square zero. meaning that if something wrong done with this mixer, right? The attacker will know who is the sender, who is the receiver, right? Make sense? So what is the solution? But before that, I'll explain to you what is the solution. Let me explain to you why it's called mixer. So suppose that we have one mixer, okay, one proxy in the middle. It's called mixer because it will receive different messages from different centers. It will mix it, shuffle it, right? Randomize the order, and start sending out the packets. Okay. So now, assuming that the mixer is trusted, nobody can actually get the private key of this mixer. What we are achieving, what we are seeing as adversary from outside the world, that A, C, and D, or the senders, are sending some messages to the mixer, and there are some packets going out to B and E, right? So we don't know whether A is communicating with B or E. We don't know whether C is communicating with B or E, and so on. So we are achieving relationship anonymity, aren't we? So in other words, the mixer does achieve the anonymous relationship anonymity. In addition to that, it will nullify this timing and size attack by doing some the mixing of packets and shuffling the order at which it was received and sent. Now the problem is, before I talk about the anonymous return address, let me again go back to the question that I asked you. What happens if this mixer was compromised? What should we do? Hashabah.
What do you mean by what we should do?
What is the solution? Give me a valid, a feasible solution. If this mixer, let's say, is compromised, somebody knows it's the private key. So once we know the private key of this mixer, then we can decrypt this message, decrypt this message, decrypt this message. Immediately know what is this receiver, right? So we know who is sending to whom. Now, what is the solution? From the name, mix network. So rather than using one mixer, we can use a number of mixers, right? So we're gonna do cascading. So rather than using just a single mixer, we're gonna use a number of mixers, or a chain of mixers, or a network of mixers, and hence the name mixed network, right? So in fact, it has been proven that if you have a mixed network, even if all the mixers are compromised except for one, it will suffice. It will still, preserve the anonymity of preserve the relationship anonymity. That's why you see, if let's say we have 3 mixers, 2 of them were compromised, then a single one will still guarantee this relationship privacy or relationship anonymity, right? So what stops us from having a large number of mixers? What do you think? Obviously, if we have a large number, what is that?
Efficiency.
Efficiency, exactly, or performance, right?
Yes.
Because and then we just need to encrypt how many layers?
Number of mixers.
Number of mixers. In other words, if we have a big network, then we need to establish a link between the sender and receiver. Depending on the size of that link, we need to encrypt. Let's say if the number of hops in that network is n, we need to encrypt the message with n layers of encryption, right? So we have a lot of encryption decryption to do in this network. Obviously, the larger the number of networks, so the mixers in the network, the more robust against attacks, right? Now the question is, how can we return an address? So for example, let's say A is sending to Bob, Alice is sending to Bob, Now Bob received this message and he wants to reply back to Alice. And of course, you know, Bob doesn't know who is the sender, right? Okay, so in this way, Alice is unless Alice explicitly mentioning that, you know, I am Alice, I'm sending you something. Bob doesn't know who is the sender because it's coming from the mixer. Now, if we want to have this, the sender is anonymized. How can we assure that Bob is able to reply a message to Alice? The idea is as the following. Now, remember, Alice is being anonymized, right? So Bob doesn't know who is the sender actually. So in order to achieve that, on top of the message that is being sent by Alice, he will or she will append two things. Some random public key that she generates, let's say PK2, and her address, which is A, appended with some salt, encrypted using the mixer public key. And the whole thing is kind of appended or encrypted using the mixer public key. Now this whole packet is sent to the mixer. Now the mixer will encrypt. She will get the mixer will get this. Then will forward this message, which is the encryption of PKB R0M, encryption of using PKM S1A, and it will send also PK2, right? PK2. It will send to Bob. So Bob will receive the entire message. Obviously, Bob will decrypt it using his secret key. He will get the message, but he will also get two more things, which is some random public key, PK2. I'm saying random because it's Bob will do nothing, but will not use it for any good other than returning a message, and some the address, which is the recipient, but encrypted using the public key. So now does Bob know who is the receiver of this return address or receiver of this reply message? No, because it is encrypted using the public key of the mixer, right? So now Bob, if you want to respond, right, he will use that public key sent by Alice in order to encrypt the response along with some salt, right? And he will send it. He will also on top of that he will send the encrypted sender or the encrypted recipient of the message, right? So now when the mixer received that, he will decrypt this, and he found out, oh, the address is A, right? And he will get some encrypted message, and that will be forwarded to Alice. So Alice now, using the public key that he generated, okay, he will, obviously there is a private key, so he will what is that? He will decrypt this. I don't just a minute. Oh, actually, yeah. I'm sorry. There is something missing. Okay, I think this is an extra. Okay, there is no double encryption here. So the mixer will send only the packet or the encrypted packet using PK2, right? That include the response from Bob to Alice. So Alice, basically, he will just decrypt this message, and he will get the response message, right? So I think there's something missing here. I apologize for this, but you see, the idea here is as the following. The idea here is for Alice to provide the return address to Bob. Alice will generate some random public key, okay, that only she knows. When I say random, I shouldn't say random. I should say one time only, one time public key, right? And we'll send her address encrypted using the mixer public key. and that will all sent or delivered to Bob, where Bob will use that as a way or a mean to tell the mixer that this is the guy, this is the this is the receiver of this message, which is encrypted using the public key that Alice generated as a one-time only. Okay. So obviously, even if we have a mixer or a chain of mixers or a network of mixers, then we still can achieve this return address using a cascade or using a chain of mixers, right? So in other words, we're gonna have, if we have, let's say, 2 mixers or 3 mixers in the middle, we will have how many layers of encryption here? We have as many as the number of mixers that are in the middle. Okay. So obviously there are some consideration that we need to take care of when we design such mixed network. In order to like kind of prevent any kind of attacks, all the messages has to be the same length. It has to be all of them has to be obviously encrypted using the same encryption scheme, so that it will become truly random. The mixers has to randomize the order of output, so they will receive a batch of inputs, and rather than sending out the messages in the same order it was received, no, it should randomize the order. Obviously, if we have a mixed network, then the protocol that these mixed networks has to agree with each other in terms of encryption and decryption order, right? Now, there are some practical consideration when we discuss or when we create such a mixed network, and that is coming from the batching strategy. So there are some decisions that we need to make on how long should we wait, or how many messages should we collect before starting sending the output, right? Also, in the same time, if we collected enough messages, right, how can we select which message to send for next? And this is a problem, or these decisions it has to be kind of carefully designed in a mixed network to kind of prevent any type of timing attacks and packet size type of attacks. Okay, so there are actually some practical networks that is being implemented using Chom's network, but again, it is in a very limited setup and scenarios. So next class, inshallah. So this is it for today's lecture. So as a summary, we talked about cipher or anonymous remailers, right? Specifically type 0, which is pseudonym remailer, and type 1, which is cypherpunk remailer. And there are also this mixmaster and mixminion. And in fact, cypherpunk remailer is just an example of a bigger network called Chom's mixed network, right? Where it's actually kind of a conceptual network. Well, I wouldn't say conceptual network, but a network routing protocol that kind of guarantees the relationship anonymity between the sender and receiver, and it obviously uses cryptography or encryption in order to kind of hide the identity of the senders and the receivers. So next class, inshallah, we'll talk about what is called the onion routing, okay, OR, onion routing, which is kind of a specific another enhancement of routing protocol on top of mixers or Chom mix design. And then we'll talk about Tor, which is kind of an enhancement over onion routing, which is used to anonymize the networking. So it's kind of one at least one running network that allows you to browse websites or web pages anonymously, as well as to avoid any censorship on top of the public internet. Any questions? So next class, inshallah, we'll talk about this onion routing as well as the Tor, T-O-R, Tor network, and we'll see how Tor network actually works and what is the change, what are the differences between OR onion routing and Tor. Any questions? Okay, if you don't have any questions, so I think I'll stop now. Let me know if you have any. So I'll stop the recording. I'll be around if you have any kind of private